Have you ever stopped to wonder why molecules have the exact 3D shapes they do? You know, it's not random at all. Today, we're going to pull back the curtain on hybridization. It's this really elegant theory that unlocks the secrets behind the geometry of pretty much everything around us.
Okay, let's jump right in with a classic chemical mystery. If you just look at a carbon atom's basic electron setup on paper, all the rules suggest it should only be able to form 2 bonds. But then you look at methane, CH4, and, well, carbon is very clearly bonded to 4 hydrogen atoms. So what gives? This exact puzzle is what forced chemists to completely rethink how bonding actually works.
So to solve this little mystery, we need to make sure we're all on the same page about how atoms connect in the first place. Let's just do a quick refresh on the absolute basics of bonding.
At the very heart of all of this are things called atomic orbitals. Now, don't think of these as little planets orbiting a sun. They're more like fuzzy clouds, the specific areas where an atom's electrons are most likely to be hanging out. A chemical bond is just what happens when the electron clouds of 2 atoms overlap, creating a new, bigger, shared space for those electrons called a molecular orbital.
Here we're looking at the simplest bond you can possibly imagine. On the left, you've got 2 separate hydrogen atoms, each with its own little spherical 1s orbital. When they get close enough, those orbitals smash together, head-on, to form that single sausage-shaped molecular orbital you see on the right. We call this really strong direct overlap a sigma bond.
So why do atoms even bother doing this? Well, this energy diagram tells the whole story. The separate atoms are at a higher, kind of jittery energy level, but when they combine to form that sigma bond, they drop down to a lower, more stable energy state. Nature is always looking for the most stable, lowest energy option. It's like a ball rolling downhill. So forming a bond is a big win for the atoms.
All right, now that we've got the fundamentals down, let's get back to our carbon problem. That simple overlap model just doesn't explain methane. And this is where scientists had a truly brilliant idea, a new concept that changed everything.
They called it hybridization. The core idea is that before an atom bonds, it can take its existing orbitals and kind of mix them together, like a painter mixing red and yellow to get orange. The atom creates a brand new set of identical hybrid orbitals that are just perfectly shaped for better bonding.
Now there are a few basic rules to this game. First, you get out what you put in. If you mix 4 atomic orbitals, you get 4 new hybrid orbitals. Simple. Second, this whole idea only makes sense when atoms are actually forming molecules. It doesn't apply to a lone atom floating in space. And finally, those strong covalent bonds we see are formed when these new, improved hybrid orbitals overlap.
Okay, armed with our powerful new theory, let's reopen the case file on methane. Let's see if we can finally crack this thing. So the theory goes like this. Carbon takes its main bonding tools, its outermost orbitals. That's 1 spherical 2s orbital and 3 of those dumbbell-shaped 2p orbitals. And as you can see, they all start at slightly different energy levels. And then it just blends them all together. This energy diagram shows it happening. They merge and average out, creating 4 brand new, totally identical orbitals that all have the exact same energy, which is somewhere in between the original s and p levels. Now, since we mixed 1s and 3 p orbitals, we logically call these new creations sp3 orbitals. And because electrons all have a negative charge, they want to be as far away from each other as possible. So these 4 new orbitals naturally push each other apart, snapping into this perfect, symmetrical tetrahedral shape with an angle of 109.5 degrees between each one. And here's the payoff. In methane, each of carbon's 4 new sp3 orbitals is perfectly set up to form a strong sigma bond with a hydrogen atom. It creates 4 identical, stable bonds. The theory perfectly explains the reality we see. And just like that, case closed.
But that's just single bonds. The world is full of more complex molecules. What about double bonds? Let's open up our next case file and see how the theory holds up.
So, the next big challenge is a molecule like ethene. It's got a carbon-carbon double bond. Our sp3 model was perfect for 4 single bonds, but that's not going to work here. To get a double bond, we're going to need a different hybridization recipe.
For this to work, carbon gets a bit more selective. It only mixes its 1s orbital with 2 of its p orbitals. This creates 3 new sp² hybrid orbitals, and this is the really crucial part. It leaves 1 of the original p orbitals completely untouched or unhybridized. And what do those 3 sp2 orbitals do? You guessed it. They push each other as far apart as possible, forming a totally flat triangular shape. We call this trigonal planar.
The angles between them are a perfect 120 degrees, and these orbitals form the strong, underlying sigma bond skeleton of the molecule.
So what about that lonely p orbital we left behind on each carbon? Well, as you can see here, they end up sticking straight up and down, perpendicular to the flat plane of the molecule. They're lined up perfectly parallel to each other.
Because those p orbitals are so close and so parallel, they can overlap, but in a new way, sideways. It's not that head-on collision like a sigma bond. It's more of a side hug that happens above and below the main bond. This sideways overlap creates a second, different kind of bond called a pi bond. And there you have it. One strong sigma bond plus one pi bond equals our double bond.
And hey, don't just take my word for it. The data backs this up completely. This chart shows a really clear trend. A double bond is way stronger and shorter than a single bond. Why? Because you have two bonds, the sigma and the pi, holding the atoms together now. And look, the trend continues for triple bonds, which are even stronger and shorter still. It confirms our model perfectly. So we've solved the puzzle of single bonds and double bonds. But why does any of this really matter? What's the big takeaway from all this abstract theory?
Well, the answer is that hybridization isn't just for explaining things we already know. It's an incredibly powerful predictive tool. It's like a crystal ball for chemists. By figuring out the hybridization of the atoms, they can map out the precise 3D shape of a molecule before they even step foot in a lab.
And that right there is the ultimate takeaway. A molecule's shape is everything. It's its destiny. That shape dictates whether a drug will fit into a protein in your body, why something tastes sweet or bitter, or how strong a new material will be. Function always follows form, right down to the atomic level.
I mean, when you think about it, everything around us is governed by these invisible geometries. The medicines that heal us, the very air we breathe, it all comes down to molecular shape. And it leaves you with this amazing thought. If we understand the rules of shape this well, what kind of future could we build by designing new things one molecule at a time?